Hello everybody, and welcome to our video on Introduction to Integration. And we're going to continue now with some examples of integration applications. So first, if we're given the derivative of a function and we know a fact about the original function, then we can write the original function. So if I start with the integral of 3x squared plus 2x, I can split that up and take the integral of each function separately. Remember, it's important to write this dx part. That's just telling you what the variable is that you're taking the integral with respect to. I can factor out these common factors here, or these coefficients, I should really say. And then I can take the integral of x squared, which is 1/3 x cubed, and the integral of x, which is 1/2 x squared. And I can simplify by canceling out these factors, and I end up with x cubed plus x squared plus c. And that seems to make sense because if I take the derivative of this function, I would end up with 3x squared plus 2x. But I don't know the value of c. I do know some information, so I can find the value of c and actually get an official function. Okay, so I'm going to plug in 2 to my function here. 2 cubed plus 2 squared plus c. And I know that if x equals 2, then y equals -3. So I'm going to interchange that for -3. I'm going to solve for c and get -15, and that means that my function, my original function that gave me this derivative is x cubed plus x squared minus 15. So I can find the value of c if I have some information. I'm also going to look at this one here, and I apologize for the, it's a little bit blurry. We'll do the best that we can. Okay, so part B, we know that a curve passes through this point. Again, that's like knowing that f at 32 equals 30. And the gradient of the curve is given by f prime of x. So that is the derivative. So if that's the derivative, I can rewrite that as x to the -3/5. I can take the integral of that function. Remember, I'm going to add 1 to the exponent and multiply it by 1 over n plus 1. So if I add 1 here, I'm going to get 2/5, and I'm going to multiply it by 1 over 2/5, which is the same as multiplying it by 5/2. And then, so I have my skeleton equation, if you want to think of it, for my function, but I need to figure out what c is. Luckily, I can plug in. I know that f at 32 equals 30. So if I plug in 32 here, and I can take the fifth root of 32, which is 2, and square it to get 4, times 5 is 20, divided by 2 is 10, plus c. I set that equal to 30, because that's the information I was given, and I find out that c is 20. So my function is 5/2 times 2/5, x to the 2/5 plus 20. Okay, my last equation, the rate of growth of a population, is given by this derivative. We have an interval 0 to 5 years. The initial population was 200 fish. Find the number of fish at 4 years. So for this one, I'm going to take the integral to find my population function. This is the rate of change of the population. So to find the initial population, I'm going to take the integral by pulling out that 150 coefficient, taking the integral of t to the 1/2, which is t to the 3/2, times 1 over 3/2, which is the same as multiplying by 2/3. I'm going to simplify that, and I'm going to plug in. I know my initial value, when t was 0, my initial value was 200, so they told me the c value. And I'm going to plug in 4 for my t value for the number of years, and I'm going to find out that after 4 years, there are 1,000 fish. Thank you. Continue to the next video.